Well, this is the microprocessor board for the bump shaker table. I made a new version of it so I could demonstrate it to you. It works, but I have to tell you, this project is a bit of a job. Nonetheless, if you're brave and you have other resources available, perhaps you can get this to work. You may need some help from a local high school or community college. They often can help a lot with these kind of things. Anyway, this is LilyGo T-Display S3. It uses an ESP32 micro on it, and I put it on a little piece of vector board. And I'm going to describe the whole process to you in this video. I hope you enjoy. All right, so let's get down to business. What we have is a LilyGo T-Display S3. S3 is the type of ESP32 that it uses. The ESP32s have a whole bunch of different varieties now that do different things. We don't need to worry about that at all. The S3 is a really nice one to use for various reasons. So these displays are really quite beautiful. Let me plug this in to power. And you can see I've just programmed up a little example, this meaningless, but you can see what you can do. Multicolor, very beautiful display. So what we're going to do is we're going to put this display with the microprocessor on it onto this vector board. And I'm going to use pins and sockets. I'll put the socket on this board, and the pins will get soldered to here. You can actually buy a version of this with the pins already soldered on, which I highly recommend. I didn't do that because I didn't know you could buy it that way. All right, so that's the story with this. Then this display will go through a hole in the case that I use for this project, and we'll be able to see the various numbers that we're using to control the shaker table. So here's the schematic. There's actually nothing to do on this piece of vector board except wire it so that we can get access to the pins that we need. There's no other components. So first of all, we're going to have some adjustments. We're going to have a pot that adjusts the frequency of the shake. We're going to have a pot that adjusts the amplitude of the shake, how much force we apply. And we have a pot which I call forward back, and that is the percentage of energy that I use, or power, the power on the motor that I use to drive it backwards or drive it forward into the bump. I don't know if this is going to be useful or not, but I'm going to put it on this one because I'm curious to see what it does. This board is fed with 5 volts, and of course there's a ground that comes along with that. And the board itself makes 3 volts. So there are 2 3-volt outputs, very convenient, and we're going to use those. We use one of it's actually 3.3, but that's okay. It says 3 volts on the board. We're going to use the 3.3 volts to drive the pot. So for instance, there's a 3.3 volt connection, and that goes to the pot. There's 3 pots, so we need 3 of those. That's nice. We also have 3 volts going over here, which I'll describe in a minute. The potentiometer needs a ground, so there's a ground connection. Here's a ground connection, and here's a ground connection. And then as you change the setting on the pot, this wiper moves up and down, changing the voltage on that line. So we bring that voltage back into the board, and it's going to get sensed by the microprocessor in an analog to digital converter that's inside the microprocessor itself. So we have 3 of those for our 3 potentiometers. On the other side of the world, we need to drive that H-bridge switch. And the only actual control we need is called the left PWM or the right PWM. And we'll take a look at that in more detail in a minute. There's a ground connection, of course, to that board. And there is a 5-volt connection. There's a 5-volt connection, which comes from this 5 volts over here. And that goes to the H-bridge switch. And there's also a couple of 3.3 volt lines which we need to enable this H-bridge switch. So if we don't enable it, then nothing's going to happen. So we need to make that connection. And we could do that over on the switch module itself, but it's probably easier to do it here. So I'm going to add connectors for these pots and for these 6 lines that go over to the H-bridge switch, because I like to be able to plug things in and out of this board if I ever have to remove it to modify it. I may want to use more of these inputs or outputs someday. Now, the way that we talk about the I/O on this is through a term called GPIO. It stands for General Purpose Input or Output. Almost all of the pins on the ESP32S3 can be used as either inputs or outputs. They're totally programmable. As it happens, though, internally, GPIO pin number 1, which is this guy right here, is internally connected to an A to D converter. Happens to be connected to channel 0. There's 8 or 10 channels of input for each one of these A to D converters. It's just a big multiplexer, a selector. So we have available on this board GPIO 1, 2, 3, 10, 11, 12, 13, 16, 17, 18, 21, 43, and 44. There's a lot more GPIO on the ESP32 itself, but this module happens to only bring out those GPIO. So if you buy a more general purpose ESP32 microcontroller board, you'll have access to a lot more I/O if you need it. In our case, we're not even going to use what we have available here. 3 we probably don't want to use because it's called a bootstrapping pin, and it changes the behavior of this thing when you turn power onto it depending on whether you have it connected or not. So let's not use that. Otherwise, we can use any other ones of these GPIOs that we want. There's no restriction. There's kind of a dedicated function called transmit and receive for a particular I/O protocol, but it's still general purpose, so we could reprogram that to do whatever we want. Anyway, we're not going to use that. What we need is right side PWM, left side PWM, so R and L PWM. We need the input for our frequency control pot, our amplitude control pot, and our forward-back control pot. So really we only need these 5 I/O lines, and these 2 are dedicated outs and these 3 are dedicated ins. So I got my piece of vector board, got mounting holes in the corners. Remember, we're going to mount this thing up against the face of the case, or the front of the case, or however, so that this guy is, out. We can see it. Okay, so now I've engaged these pin and socket things, and I'm going to place that on here. All right, now I got it set up for soldering. I don't know if I can actually show you what I've done. That's in there, but nothing is soldered. So I've engaged everything, and that's important because we don't want to solder it kind of in a way that it won't fit back together again. All right, I've got my soldering iron set up here. Now I've got some 0.6 millimeter rosin core solder, and I've had cataract surgery, so I can't focus, so I have to use this. This is Optivisor. And I now just solder, making sure that it's not going to rock back and forth. I'm going to solder one pin on here. Let's choose this one. And now that should stabilize. Yeah, that stabilized the whole thing, of course. Okay, so let's do that corner. Let's do this corner. And we'll check. It feels fine to me. All right, I have all of those joints soldered. Now I've got to solder this crazy thing on. I've got to get solder down into there. I know I can do it because I've done it before, but it's a bit of a pain. All right, so there's the solder job. I'm going to do a very careful visual inspection to make sure I don't have any cold solder joints, because that can lead to unpredictable failures in the future. Everything looking good there. And now I just got to do that side, so let me do that. Everything's soldered up. Now I can just remove the board and put it back in. Okay. Now I'm going to add pins for the connections that I want to make to the external world, which of course are the pots and to the H-bridge switch. So let's do that. All right, so here I have some pins. I have 3 pins for each pot, and I have this 6-pin connector that goes to the H-bridge switch. So let's do the pots first. So this is the bottom view, and this is the bottom view, so I know the pot connection should go up here. And I'm just going to put them out here to the edge of the board. Always clean the tip of your soldering iron with water. I use a sponge, and you just do that. So there we go. I got that one. I'll put this one on next. I've got all the pins mounted. Wasn't too bad. So all soldered on this side of the board, there, and sticking out that side so that when we mount this down to the case, we have easy access to all this to plug it all together. Now, the way you might think of wiring this up is by stripping a bunch of wire. That works. You can take bits of wire, strip them, and make the connection. I like to, for as much of the wiring as possible, I like to use just this 28 gauge tin-coated bus wire. Why? Because I don't have to strip anything, which is actually the longest part of the project. So let's see how much I can wire it up without using any insulation on the wire at all. So let's wire up this line. 3 volts, which is this pin here, goes to, sorry to point the finger at you, this pin is 3 volts, and it goes to here, here, and here. And of course, those connections are made on the back side. So, I mean, you can do this board any way you want to, but this is the way I like to do it. So I am going to stick the wire through that hole. It comes out there. I just fold it over both ways, and I'm going to solder that right there. I don't know how well you can see that. Let's zoom in. Okay, all wired up. It's not the prettiest soldering job, but I've ohmed it out and it's all perfectly okay. So here's the port that goes to the H-bridge switch. 3 pots. This is the 5 volts in. All right, so I got potentiometers in the mail last night from Amazon. I got some other parts too. We'll open up a bit later. So these pots go right on to there. It's very convenient. I hope they all go on there. Yeah. Okay, so and we can change the orientation, in other words, the direction of what's up. We could do that in software, but it's nice to have the option of just reversing the connector to change the direction of the potentiometer. I've also wired in a little voltage divider here. There's a 27K and a 4.7K. It gives you a voltage divider ratio of 6.5 or something. That lets me put a PWM voltage on here and measure it, or at least display it, right? And the same here. So I've got 2 input ports that'll accept a voltage and will display it. I have to put the voltage divider here because the micro only goes up to 3.3 volts. And if you put more than that, you can blow it up. And you will. So you got to be careful not to do that. So that 6-to-1 voltage divider will let me put in something like, what, up to 18 volts, and so that'll be very safe. Okay, so I got the code in it, at least part of the code. The part of the code that reads the pots and displays stuff. So let's go through what that looks like. So here's the frequency adjust pot. The range, you can see it here. The range is 3 hertz to 9 hertz. This is the amplitude adjust, 0 to basically 100%. And this is the kind of the forward to back ratio of force, if you like, and that's also 0 to 99.9% or 100%. So, and the voltage, the 2 voltage inputs are here. I don't have a voltage on it, but I've checked it and they both work. I've called them PWM 0 and PWM 1. The next step is to actually now write the code that produces the output, and the output has to be the left PWM or the right PWM. Left meaning I'm going to move the table to the left, or put force to move the table to the left, and I'm going to, and right PWM means put force to the right, and that's down here. So these are the 6 connections to the H-bridge switch. Left PWM and right PWM are the only active ones that need a control from the microprocessor. Well, there's the finished board. I've got 2 scope probes on it. Everything is on. It's being powered from 5 volts. And there's the finished project. And it's all working. It was quite a job. There's these boards with microprocessors on them, the documentation is poor, so I had to go looking around the internet to find why some things weren't working. It took hours this morning to actually get this to work after I had it all wired up. So changes in code and so forth. So anyway, let's take a look at the oscilloscope and watch what it does. All right, so the top trace is the motor going one way, and the bottom trace is the motor going the other way, or force being applied anyway. So that can be changed with this. I have to let the scope acquire. I'm changing the forward back duty cycle, and you can see how that works. And what you're looking at in here is the pulse width modulation. So one period is from there to there. This plus that is one period. So I can change the period, can change the frequency of operation, make it much slower. They're slower, that's 3 hertz. And I can take it up to 9 hertz. And that's 9 hertz. Okay, so let's go take a look at what's inside of one of these fuzzy things. I can zoom in on something. And we'll do a single run. So what that is the amplitude set at 73%, so it's on for 73% and off for the remaining time. And this one of these little cycles is at 8 kilohertz. So this is very fast with respect to the shaking of the table back and forth. So that kind of averages out in the motor, and it gives you 74% of the amplitude. So if I change that, I'll put it down to like 13%. We'll run it, and then we'll stop it so we can take it. Now you see that it's only on for 13% of the time, and it's off for the rest. So that's the operation of the thing. And of course, both channels are doing the same thing. But I can't display both at the same time because one is on and the other one is off. That's the way the H-bridge switch works. So here's the code for the module. I'm not going to discuss it today, but I will make a video about it, and we'll talk about that. I'm going to end this video now. It's long enough. So see you next time, and thanks for watching.